and go from current slide. Okay, before we get started, while the projector's coming up, just a couple of things. I think I had told you last week they had published final exam schedule, and I thought it was wrong, okay, because it doesn't agree with the academic calendar, it doesn't agree with the administrative calendar. They had us having final exam starting next Monday, and everything else says next Tuesday, okay? So I had emailed the dean who sent it out, and as far as I know, got no response. No one else heard any changes to it. But then I talked with my boss, who's the associate dean, on Friday, and he said, oh yeah, that's wrong, but since it was published this way, they're letting each instructor decide. So we are having class on Monday, and I'll give you the last test, which is the final, on Monday at the end of class. So we have class today, class Wednesday, and class Monday.
When will that be too?
Okay, you're not graduating this term, are you? Okay. If you're graduating this term, it has to be in by Thursday. If you're not graduating this term, the following Monday. But anytime sooner will be fine too. Okay. But yeah, that's because grades are due in for graduates on Friday at noon, and for the rest of the students, they're due in Wednesday at noon. But final exams are technically over with on Monday. Now, I will take it on Tuesday of that week, but don't make it the end of the day. So I have to get them graded, all the grades in, and everything on Blackboard, on the suite, and everywhere else. So it takes a while to get all that done. So for just graduates, there's usually not that many. I can get those done in a day. But for everybody else, and in many classes, many people have stuff they haven't turned in yet. So
I do. I got a test.
Yeah, well, you're in better shape than most. Okay. So where we left off last time, we had gotten to the place, this is, if you recall, what we're doing, we had this, and they've called it the auxiliary equation. I want to make sure they come up with that term for it. When you have, let's back up a little further. When you have a linear equation with constant coefficients, not functions of x, constant coefficients, okay? And we'll start with the case, the homogeneous or homogeneous case in which it's equal to 0. The differential equation is equal to 0. All the coefficients are numbers. Then your assumption is, and it makes sense, the solution has to be of the form e to the mx. So when you do all the derivatives and stuff like that, what you wind up with, the factor e to the mx times a polynomial, depending on how big your, what the order of your differential equation was. Okay, if it went up to order 7, then you have a sub 7 plus a, you'd have, you have m to the 7th, m to the 6th plus m to, you'd have terms with each one with different coefficients, and then you have to do factoring, sort of like we did back in pre-calculus algebra, okay, finding the zeros. Okay, now, we're right now settling on just for order 2 or higher, for right now, okay? So second degree polynomials and, second order differential equations, okay? So when you do that, you wind up with a polynomial in M, okay? Now, if you can factor it, then case number 1 on page 136 held. If you can factor the thing, you came out with distinct real roots, okay? In fact, they're distinct rational roots, if you can factor it. But if you can't factor that quadratic equation, then you use quadratic formula. And if you come out then with irrational roots, still 2 distinct real roots, okay? Those are the easy ones. Now, case 2 was if you came out with repeated real roots, okay? Now, this was the one, since we're only dealing with quadratics here, that would be x plus 1 times x plus 1, okay? So it's x plus 1 squared. So you have a repeated root of minus 1. Well, then you do an additional factor, and that's what we did last time. The first one would be e to the m1x, next would be c2 x e to the m1x. So that was the second case. The third case was, what if that discriminant, remember the thing in a quadratic formula that's in the radical? If that came up negative, now you have complex roots. You have i's in there, okay? And here is what typically your equation would look like, okay? Y is equal to C1. Now, here they put capital C's, and I don't know why they do that. I guess so you don't confuse them with complex numbers, which are usually little c1, yeah, but whatever. C1 e to the, and if you came out with complex roots, it's going to be of the form alpha plus I beta, there's the complex part, times x, plus C2, because these always come out in conjugate pairs as long as you have real coefficients of your differential equation, and that's all we're dealing with. We're not dealing with complex differential equations. They're all real coefficients. So the second would be C2 e to the alpha minus beta I x. Okay. Now, remember, if they were two distinct real roots, then this is just a number, that's a different number. And that's your answer right there. Okay. That's if they're real. Okay? Not complex. You just have a number here and a number there. If you wind up with the same repeated real root, you have one with a number here and the same number here, but you have to put an x as another factor in there. And that gives you that. That's case 2. Case 3 is going to be complex numbers. I put the I in front there, the second there. It doesn't matter where you put your I. In the book, they put it where? In front, I, B. Yeah, I was looking at the book the first time, but I didn't on the second one. It doesn't matter where you put it. Now, here's something that's interesting. I think I wrote this down last time. In practice, we prefer to work with real functions instead of complex exponents. To this end, we use Euler's formula. E to the I theta is equal to cosine theta plus I sine theta. Now, that may look like, wait a minute, we're still going to have an I in it, okay? But at least we get one real number out of it. So if we take what we have there and use Euler's formula here, let's see what we get. Now, remember, well, let's just do it, okay? And this may get tedious after a while. I may just quit and say, well, here's the solution. But let's say y is equal to C1 e to the alpha x e to the I beta x. Okay? Remember, if you are multiplying powers, you add the exponents. So I just did it reverse. We added the exponent, I multiplied the powers. Plus C2 e to the alpha x e to the minus I beta x. Okay? Now, let's take this one.
Sorry, which one are you looking at?
Okay, no, I'm trying to fill in the blanks of what they skipped in the book.
Oh.
Yeah, this is how they get from here to there. Okay. Now, this would be y is equal to C1 e to the alpha x. No problem there. But this one right here, we're now going to write as, this is e to the I. Now, beta x is going to be theta. Okay? That's just, that's what we're going to use here. So this would be cosine theta, or let's do beta x for now, okay? No. I went to erase and now forgot to erase, and we're going, at some point, yeah. So this will be e to the cosine beta x plus I sine beta x plus C2 e to the alpha x. And then this one, e to the minus I beta x, will now be, in this one, your theta is minus beta x. Okay, it's the I theta here, I minus I beta x here. So this will be cosine to the minus beta x plus I sine to the minus beta x. That's really made it a lot clearer, hasn't it? Okay. Just plugging in what that is. Now, just a little bit of note here. Because cosine is an even function, cosine minus beta x is the same as cosine beta x. Okay? Remember, even function. Any cosine does like this, those two are the same, whether it's minus or plus, they have the same value. Sine is the opposite, because sine does like this. This is the opposite of that. So, these will have, this to be written just like this, okay? But this one will be written with a minus sign, okay? So, if it's okay, I'm just going to do that. That's going to be the same. This is going to change that minus, that plus to a minus. And, oh, I should have taken that out while I was taking. Okay, yeah. Now, hopefully that wasn't too bad of a shell game there. Oh, yeah, that became a plus. You just can't tell. Okay, plus. So those two are now the same. Okay. Now let's see what we've got here. We've got a C1 e to the alpha x cosine beta x plus C1 e to the alpha x. I'm going to put the I in front. Sine beta x plus C2 e to the alpha x cosine beta x minus C2 e to the alpha x sine, we'll put the I in front, beta x. Okay. Whew. Okay. Now, and you'll see in the book it says where cosine minus beta x is the same as cosine beta x, so that's why we did that part. Sine minus I beta x is minus sine beta x. And note by the first adding and then subtracting of the two equations in example 7, so what we're going to do is okay, they took just these two, this one and that one, not with the C2s in them. They first added them together and then subtracted them, okay? and they pull another switcheroo on us here, and they say these are true for any C1 and C2s, okay? So they're going to say the choice is C1 equal C2 equal 1. So when you have this C1 and that C2 both equal to 1, okay, what do you have? E to the alpha x cosine beta x plus I e to the alpha x sine beta x plus, oh, this is 1, remember, okay, 1, e to the alpha x cosine beta x minus I e to the alpha x sine beta x. Okay, those are when C1 equals C2 equal 1. Okay, just as long as they're not 0. They're, okay. Well, look at what we've got here. These two terms are exactly the same. These two are exactly opposite each other. So in that case, you wind up with no more room on the board. So I think I'll come up here and erase these two, if I can get away with that, okay? And what we have here, when those are equal to each other, your y is equal to e to the alpha x cosine beta x. This one plus that one, just 2 of them, okay? Because these two added to 0, okay? Now in the second case, they say let C1 and C1 be 1 and C2 be minus 1. Well, in that case, you get y is equal to, now here, this one is 1 and that's a minus 1, so these two go out and these two become 2. So you have y is equal to 2I e to the alpha x sorry, sine beta x. Why it shuts down, I don't know. Okay? Now, those are the two conditions we have here. Okay? And this you'll find, now they're calling this y1 and this y2. Okay? Now, now they have somewhere here from corollary 1A of theorem 4.1.2, and I'm going to have to go back a ways to find that one. 4.1.2, this is going to be early in chapter 4. There it is. The corollary. This is bottom of page 122. A constant multiple is also of a solution y1 of a homogeneous linear differential equation is also a solution, and a homogeneous linear differential equation always possesses the trivial solution y equals 0. Well, we hopefully won't need that one. So what we're going to do here is magic, because they take these two solutions and say, lo and behold, and here's what I'm thinking they're going to do here, because they don't say exactly how to do this, but my guess, if you multiply this second one by I, which would be a constant multiple, then you wind up with a real solution. Okay, now they didn't say that, but this is how they then determine here, and this is the bottom line for case 3. Here are your solutions. Y is equal to, now this is why they use capital C's before, because now these are little c's. C1 e to the alpha x. You know, that was always in the case. In both cases, they were always in there. E to the alpha x. Okay? Cosine beta x. And that was from this one up here. Okay? Alpha x, beta x. They're leaving off the 2's. You know, you could divide those out, include that with your constant. Here's the sort of magical part, plus, let's see, yeah, C2 e to the alpha x, notice that in there, okay, sine beta x, okay. Now, if you pull out the e to the alpha x, because it's common in both of them, you have C1 cosine beta x plus C2 sine beta x. So, if you wind up with your discriminant of your quadratic equation there, negative, that gives you your beta. Flip it around and make it positive, and that's your beta. The alpha is what you have out front. Remember, it was minus b over 2a is your first part, and then your next part is plus or minus the square root of y. That's where your imaginary part. The minus b over 2a, that's your real part. Okay? M is equal to minus b over 2a. And then the imaginary part is whatever's in there. We'll flip it around so it makes a positive square root. That's your beta. The alpha is the minus b over 2a. The beta is the square root of b squared minus 4ac. But if that's negative, then make that 4ac minus b squared. Now it becomes positive over 2a. That's your beta. So whatever your real part of that imaginary number, that goes here, and the imaginary part goes there. And those are our 2 solutions. So, yeah, they look different, and they are quite different. They have alphas and betas in them, which didn't before. Well, the reason for that is from the real and imaginary parts. So when we actually do them, hopefully they'll make more sense. But that's the theory behind it. And again, I tried to, like everything, fill in as many gaps as possible, but they still jumped the shark on a couple of them that the only thing I can figure is they multiplied by I. Okay, so let's do example 1. This is an easy one, I hope. Okay, I sure hope it is. Solve the following, this has all 3 of them in it. Solve the following differential equations. The A part. 2y double prime minus 5y prime minus 3y is equal to 0. Okay? Constant coefficients, homogeneous differential equation. Okay, if you want to, you can make the assumption, let y equal e to the mx. That's what we always assume when you have this kind of differential equation. Constant coefficients like this, do that. Okay? Then your y prime would be m e to the mx. Don't you love taking derivatives of exponential functions? And y double prime would be m squared e to the mx. And then when you fill that in, you get 2 m squared e to the mx minus 5 m e to the mx minus 3 e to the mx equals 0. Right? Okay? Now notice e to the mx is common to every term. Right? And guess what? That's never 0. So you can divide it out with sound effects. Okay? Now, what do you have left? 2m squared minus 5m minus 3 equals 0. That's where your zeros are going to come. Right? Okay? What do we do with that? Can we factor? I think so. Let's see. There would have to be 2m here and an m there. If they're factorable, it's got to be like that. Now, here's where the question comes. The last term is negative, so one of these is plus and one's minus, but I may have it in the wrong place. So understand, I may have put them in the wrong place. Now, we want two numbers that multiply to be 5 and add, multiply to be 3 and add to be 5, if you put them in here. Okay, or actually the difference is 5. So my guess is let this be a 1 and that be a 3. Let's see if that would work. 2m times 2m is 2m squared. That works fine. And then you got a minus 6m plus m is minus 5m and minus 3. Yes, that works. Okay? So what does that tell you? Either 2m plus 1 is equal to 0 or m minus 3 is equal to 0, right? That's how we did our good old quadratics back in algebra, whenever that was. And when we went to solve this, subtract 1 from both sides, and that gives me 2m is equal to minus 1, so m is equal to negative 1/2 when you divide both sides by 2, right? I can't write the 2 there. Okay, negative 1/2 over here, just add 3 to both sides, and you get m is equal to 3, right? Okay, there's our two solutions. So either the first one will give you y1 is equal to, let's go on and put an arbitrary coefficient in there, c1 e to, remember, e to the mx. Well, this is e to the minus 1/2 x. There's your m. y2 would be c2 e to the 3x. So here's your solution. Y is equal to c1 e to the minus 1/2 x plus c2 e to the 3x. There it is. Take this, take derivatives, put them in, plug them back in, you'll see it guaranteed to go to 0. So that's what happens if you have either factorable auxiliary equation, or even if it's not factorable, if you use the quadratic formula and you come up with radicals that are positive, then it still works. Then you might have a e to the square root of 7x, or minus 5 root 3x, or something like that. That's fine, as long as they're real numbers, either rational numbers like these, or irrational numbers like square roots, or whatever. That's what your solutions will be. The easy case, okay? The straightforward case, okay? Just do your thing, and if you can't factor, then use the quadratic formula, okay? You remember what the quadratic formula is?
What is it? Negative b plus or minus square root of 4 minus ac.
Wait, square root of b squared minus 4ac over 2a. It's slow, but it'll get there. Okay, so that gives you two roots. As long as this is a positive number, then that will give you a real root. It may be irrational, it may have a square root in it, but it's okay. So you have minus b plus that over 2a. Really complicated number, but just a number. Or minus b minus that over 2a. Completely different number. The conjugate of it, just the conjugate of it, but still. So one of those will be your first coefficient, and the other will be the second coefficient of your e to the bottom, e to the mx. Those will be your two L's. One with the plus and one with the minus.
At what point would you start using the discriminant? I mean, it seems like you would.
Well, you use it every time. If that comes up to be a positive number, then you have this form. If it comes out being 0, then that's when you go to the second form, which I bet you is the B problem. So you want to do that one? This one, it was factorable. We didn't even need the quadratic formula. But if we had used the quadratic formula, you'd have gotten the same two numbers. It's just been a lot harder getting there. Okay? But you can always use the quadratic formula. So you want to do the second one? Okay. I think I'll erase them all if that's okay. Is that all right? Okay. Okay. So here's the second one. Y double prime minus 10y prime plus 25y is equal to 0. Now, we can go through the let y equal e to the mx and do all that, but can you come up with the auxiliary equation just looking at this? If not, we'll do the auxiliary equation. I mean, we'll do the whole smell. You'll get m squared minus 10m plus 25 equals 0. I want to do it, and I'll show you that. Huh? You do? Okay. All right. Here's how we got that. Let y equal e to the mx. That's always our assumption when you have the differential equation with all constant, linear differential equation with constant coefficients. Make that your assumption. Then y prime is equal to what? M e to the mx, and y double prime is equal to m squared e to the mx. So plug these things in. While double prime is m squared e to the mx minus 10 times y prime, which is m e to the mx, plus 25 times y, which is e m to the mx, and that whole thing is equal to 0. Right? Since e to the mx is never, ever, ever 0. Okay? Then you can divide it out. There it goes. Okay? And that leaves you m squared minus 10m plus 25 is equal to 0. Which is what we wrote down to begin with. That's your auxiliary equation. That's what they call it. Now this one also is factorable. We don't even have to use the quadratic formula. This will be m, those are easy, right? The last sign is positive, meaning these two signs have to be the same, but the middle is negative, so they both have to be negative. Two numbers that multiply to be 25 and add to be 10. 5 and 5. So here we have m equal 5, and here we have m equal 5. Well, guess what? Those are the same numbers. So this is now case 2. And the case 2...
You're saying, oh, never mind.
Yeah. This thing's equal to 0. So that means that each of those factors have to be 0, and that gives you the same number. So our solution, y is equal to C1, now we're going to put the coefficient in there, e to the 5x. But if we put plus C2 e to the 5x, hey, that's the same solution. We can't do that. But case 2, the one we did last time, remember it interjects a very simple C2x e to the 5x. That's linearly independent from the first one, yet is a separate solution. And you can go on and go back and take your first derivative of that, the second derivative of that, go through the deal, and you'll see, yep, they do come out exactly 0.
So that means if we...
Yes. You know this is there's one solution, because that was our original assumption, e to the 5x. We just put a C1 in front of it. But then, from what we did last time, we would have put a plus C2 e to the 5x, but those are not linearly independent, because they're the same thing. The numbers just wrong. They're multiples of each other. So you can't do that. So what we do is interject an x term in the second one. Just x. That's now linearly independent from the other, and if you go back and plug them in, you'll see that is also a solution. It's messy, but it's doable. You want to do it just to prove it to yourself? Huh? You do? Okay. You want to just do the C2 part? Because we know the C1 part should work. So just the C2 part.
Yes.
So, and we know those are not the same. They are linearly independent of each other. They're not a multiple. X is not a constant. It's a variable. Okay. So, let's see. C2, we'll just do that one. So, let y equal, we can put the C2 if you want to. C2x e to the 5x. Y prime is then C2. That's always going to be there. Now you got a product rule here, right?
Yeah.
Okay, so that's going to be the first times the derivative of the second, which would be 5e to the 5x. I just put the 5 out front. Okay? Plus C2.
Wait.
Okay.
Is that 5 next to the C2 right
Okay. Okay. Derivative of this. I'm taking the derivative of this.
Yeah.
C2 is there. You're doing the first times the derivative of the second. The derivative of the second is 5e to the 5x, right? So I'll put the 5 out front.
Okay. All right.
And then the second part is derivative of the first. So that's your C2. Derivative of x is 1 e to the 5x. Right?
Yeah.
Okay. Now, your y double prime, you got chain rule again on the first one, and that's going to be a 5c2 x times 5e to the 5x. I'll put e to the 5x here, multiply 5 times 5 and make it 25. That was tricky, wasn't it? Okay, that's, again, product rule. Taking the derivative of this one. 5c2, I've written those down, times first times the derivative of the second. The derivative of the second is 5e to the 5x. So I do the 5 times 5 and make it 25. Okay? That's the first. Then the second is going to be plus 5c2 derivative of the first, 1 times the second, e to the 5x. Right? So that's the second part of the product rule. And then the last one is just plus 5c2 e to the 5x. Okay? This one is 5c2 5x. Well, these two make 10, right? So let's simplify that a little bit and do 25 c2 x e to the 5x plus 10 c2 That's an ugly C, isn't it? My pen went out on me, so I couldn't see what I was. Ah! And the eraser's not working. Okay. Plus 10C2 e to the 5x. Okay. So that's our y double prime. That final answer there. So let's plug this back into our original thing. Y double prime is 25C2 x e to the 5x plus 10C2 e to the 5x. That's our y double prime that we just did. Minus 10 times y prime. Well, our y prime was 5C2 x e to the 5x plus C2 e to the 5x. Okay? Plus 25 times.
You got
Okay.
5e2x.
Okay. Right. Here's our y double prime right here. 25x e to the 5x plus 10c2 e to the 5x. Minus 10 times y prime. Well, here's our y prime. Minus 10 times 5c2 x e to the 5x plus c2 e to the 5x in parentheses. Plus 25 times y. And my y is c2 x e to the 5x. So plus 25 times c2 x e to the 5x. Okay. Now, if this thing adds a 0, we know that that's a solution. And we already know it's linearly independent from our first solution. So let's see what we got. All right. This is 25 c2x e to the 5x. Here's another 22 c2x e to the 5x. That makes 50, but minus 10 times 5 c2x to the 5x, that's going to make minus 50. Those are going to add to 0. Right? Okay? And then here we have 10 c2 e to the 5x, and here we have minus 10 c2 e to the 5x. Those two add to be 0, so sure enough, that is a solution. See it? Okay. So we've shown that's a solution. We know it's linearly independent from the first solution because it has an x in it that is a variable, so it's not going to be a constant multiple of it. So guess what? Those are two solutions, linearly independent, both solutions, and that's all you need because it's a second order differential equation. You just need two independent solutions with their coefficients. So there's the next one. So anytime you wind up with a double root for that quadratic, then put the 1 with that in, and then x times the 1 with that in. Okay? And that's going to be it. First solution, second solution. Okay? That was case 2, when your discriminant added to 0. Because in that case, if you had done the quadratic formula, you would find that b squared minus 4ac. In fact, let's do it. B squared is 100 minus 4 times 25 is 100. Your discriminant was 0, so you use your one and only one, and then do an x times the one and only one. There's your solution. Now the C case. C example. All right to erase?
Yeah.
Okay. Here we have y double prime plus 4y prime plus 7y is equal to 0. Okay. Now, do we need to go through the exercise of it, or can we just write down what the auxiliary equation is going to wind up being?
Yeah, no, we just wrote it down.
Okay, and what will it be?
M
Squared plus
e to the mx.
4m, same coefficient, 4m
Yeah.
plus 7 is equal to 0. You just put the m's and the number, the exponent of the m is going to be the number of derivative of the y, okay? And since the derivative of that last y is not a derivative, y, the derivative would be the 0th derivative, so it would be just 7, okay? Now, want to see if you can factor that one? You can. No way. No two multiples of that will give you anything close. So this time we'll have to use the quadratic formula. So your m is going to equal to, like you said, minus b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay? So here our a is 1, our b is 4, and our c is 7. So we got minus 4 plus or minus the square root of 4 squared is 16 minus 4 times a is 1 and c is 7. Okay? All over 2 times a, and a is 1. So over 2. Okay? This is going to be minus 4 plus or minus the square root of 16 minus 28. A big boo hiss here. 2 over 2, which will be minus 4 plus or minus the square root of 12, if I'm not mistaken. All right? Negative 12 over 2. Okay? Now, here's what you do with that. Minus 4 plus or minus. First thing I want to do is see if there's any perfect squares in 12 besides 1. Okay, well, 4 is in there, so I can factor out a 4. Square root of 4 is 2. Okay, but we also have the minus sign. The square root of minus 1 is I, and then what we have left over is the square root of 3 over 2. Right? All right. So this is going to be minus 2. 4 will go into minus, 2 will go into minus 4, minus 2 times. Plus, I'm going to separate them now. The 2 will go into 2 once, so it's I root 3. That's one solution. Or minus 2 minus I root 3. Okay. Now, if you remember back to our case 3, the alpha, I can't write, okay, duh. Said alpha and started writing a beta. Our alpha is equal to negative 2. That's the real part. Our beta is equal to root 3. That's the real part of the imaginary part. That's the coefficient for I. And it can be either plus or minus. So those are our alphas and our betas for this problem. Okay. Now, without having to go back and re-derive all that, we just want to go to the bottom line, which is given as equation 8 at the top of page 137. Here is your y. Y is equal to C1 e to the alpha x. That's e to the minus 2x. That's where you plug in the alpha. Okay? Okay? Actually, let me go to the second part of the bottom line there. Let's just, to keep from having to write the e to the minus 2x twice, we just want to write the 1. e to the minus 2x, pull that out, e to the alpha x, this is the second part, the second way they write equation 8 up there, times c1 cosine of beta x, root 3 times x, plus c2 sine, root 3 times x. There's your solution. Two linearly independent solutions, cosine and sine are independent. Your alpha is your coefficient, coefficient of your exponential term. Your beta is the coefficient of your trig arguments. Both of them being the same. And if you really wanted to spend some time, you could try taking the first derivative, the second derivative, and then plug all that in and carry it through and see what you get. Find out it winds up being equal to 0. Okay? Real pain in the neck, but it does work out being exactly that. No imaginary parts to it. Euler's formula gave you that form there, which then removed the need for the i's altogether. Put those as coefficients of your arguments of your sine and cosine terms. That's where your coefficients go to. So that's what you got for the C part, e to the minus 2x times c1 cosine root 3x plus c2 sine root 3x. Be sure when you write this that you make sure that your radical ends before the x. Don't put the x under the radical. Keep it out. Sometimes I like to write it cosine x root 3 sine x root 3. That way there's no way that you could imagine the x was inside that. Or I put the little, bring the house down a little bit just to keep the x on the outside. You don't have to do either one of those, but just be careful in your own working that you don't assume it's under the radical. It's not. It's always outside. Okay. And I forgot to mention the answers in the book you saw just like we had before. The first one was y is equal to c1 e to the minus x over 2. I said minus 1/2 x, same thing. Plus c2 e to the 3x. The second one was c1 e to the 5x. That's the one we did last time. Plus c2x e to the 5x. And that's exactly that. We went back and verified the second one. Let's do, unless there are questions, any questions on example 1? Let's do example 2. How are we doing time-wise? Huh?
15 minutes.
Yeah, so I think we may have time to do it. I don't think it's only one part, not 3 parts, I think. Oh yeah, this is an initial value problem. Solve this. 4, I say 4 and write y, 4y double prime plus 4y prime plus 17y is equal to 0. There's your differential equation. Linear with constant coefficients. We can use what we've just been using. But this is an initial value problem with y of 0 equal to negative 1 and y prime of 0 is equal to 2. Okay? Don't worry about those yet. Let's just deal with the differential equation. Can you write down the auxiliary equation for me? Yeah.
It's 4m squared
4m squared
plus 4m
plus 17 equals 0. Think that'll factor? Guess again. No, it will not. Guaranteed it will not. There's 17 is a prime number. It's going to be something plus 17 and something plus 1. No way you'll get that product to be a plus 4. In fact, there's no way it's going to be that I can think of, a positive number in your discriminant. But let's see. So we're going to have to use quadratic formula, which will be m is equal to What would that be?
Hang on, we're using the, I thought we were going to be using negative b, the quadratic formula.
We are ultimately, but we got to find out what it is going to be first. We got to solve that quadratic equation first.
Yeah.
So quadratic formula. Okay, minus b, is that what you said?
Oh, yeah.
Yeah. What would it be?
Minus 4.
Minus 4 plus or minus the square root of
4 squared.
16 minus 4 times 4 times 17. You think that's going to come out less than 16? No way. Okay. Over, no, not 4 squared. 2a. 2 times 4 is 8. Remember, it's all over 2a. Okay. So this is a minus 4 plus or minus square root of 16 minus 16 times 17. Actually, there is a slightly easier way to do this. Let's just write it 16 times 17. This is cheating a little bit, but it's a little easier. Divided by 8. This is to be minus 4 plus or minus the square root of 16 times 1 minus 17. Right? Divided by 8, which would be minus 4 plus or minus the square root of 16 is 4 times the square root of minus 16 over 8, which is going to be minus 4 plus or minus 4 times 4, which will be 16. These are coming up all over the place, aren't they? 16i over 8, which is minus 1/2. That's minus 4 over 8, plus 2i, or minus 1/2 minus 2i. Did you get anything close to that?
Sure, yeah.
Okay. I hope I did it right. I believe I did. Looks like I did. Yeah.
Yeah,
Okay.
it looks right.
Yeah. So, your alpha is equal to negative 1/2 in both cases here, and your beta is equal to 2. Okay? Doesn't matter whether it's plus or minus, the beta is 2. Okay. So, we can write down our solutions. Y is equal to, do the alpha first, e to the minus x over 2, 1/2 of x, that's with the alpha part, times, here's where your C1 comes in, C1 cosine, the beta is 2, so it's 2x plus C2 times the sine of 2x. Pretty straightforward, right? Now we're going to evaluate our C1 and C2 because we know that when x is equal to 0, your y has to be a minus 1. So let's put a minus 1 in for the y is equal to an e to the minus 0. In other words, e to the 0 is 1. Okay, so that doesn't contribute anything. And this gives us a C1 cosine of 0. What's cosine of 0? 1. Okay, so it gives you C1 plus, what's sine of 0? 0. So your C1 has to be minus 1. C1 is minus 1. Okay, hang on to that thought. Let's go back and plug in again. Okay, C1 is 1. So let's go to the second one, y prime. Oh boy, that means we have to take the first derivative. So y prime is equal to, good old product rule. How does that go?
We're doing it like y, right?
Yeah.
Negative x.
Okay, you're taking derivative of the first? It's fine. That's what I'm just asking. Yeah. So that would be negative 1/2 x. No, 1/2. Negative 1/2 e to the minus x over 2.
Why would it not be negative x?
Its derivative of an exponent is the exponent. So that's why that is exactly like that. Chain rule then says take the derivative of the exponent of the exponent, which is the derivative of minus 1/2 x is minus 1/2. Okay, we're taking derivative of that, just that.
Right.
Derivative of that is that. But then we've got a chain rule part, which is the derivative of that, which is,
See, I would think it would be negative x to the half.
okay, when you take a derivative, if that was x squared, then it would have been a negative x, because you take the exponent times the coefficient. Okay. Let's come down here and say z is equal to minus 1/2 x. What's the derivative of that? dz would then be the exponent, which is 1, right, times the coefficient, which is negative 1/2. That'd be negative 1/2 times x to the, reduce the exponent by 1, x to the 0. What's x to the 0? 1. No, x to, anything to the 0th power is 1. Anything. You said it earlier, e to the 0 is 1. Anything to the 0th power is 1. So this would just be 1. So it's minus 1/2. So that's why you put that out in front. Okay. So that's the derivative of the first. Okay. Times the second. C1 cosine, well, we already know what C1 is minus 1. Okay, so let's just plug that in to keep from having to write all that. Okay. Okay. Minus cosine 2x plus C2 sine of 2x. Okay, so there's the derivative of the first times the second. We just plugged in what C1 is because we already know it. And then you do plus the first, e to the minus x over 2, times the derivative of the second. Now what's the derivative of minus cosine, of minus cosine 2x?
Minus cosine 2x would be sine 2.
Sine 2x times 2.
All right.
Yeah, okay. Plus
2x.
2c2, not x. The derivative of 2x is 2. Okay. 2 sine c2 cosine 2x. Okay. Now, I hope I can go on and erase the bottom because we've already done that. Okay, use that. I don't think I need this part either, so let me go and erase all that. If we need it again, you'll tell me what it is. That's an order. Okay, no, okay. Okay. All right, so that's your y prime, is that whole thing there. Okay, and y prime, when x is 0, when x is 0, this e to the 0 is 1. So you have a minus 1/2 times, when x is 0, cosine of 0 is cosine of 2 times 0, cosine 0 is?
0.
No, cosine of 0 is?
Cosine is 1.
1. So that'll be a minus 1 plus, and sine of 0 is? 0. So that doesn't contribute anything. We've been there before. Okay. We'll close that out. Plus, e to the 0 is still 1 times sine of 0 is 0, so that one doesn't contribute anything, plus 2 c2, and cosine of 0 is 1. All right, but this thing, y prime of 0 is 2. So let's see what we've got here. This will be a positive 1/2 plus 2c2 is equal to 2. Yuck. All right, let's subtract the 1/2 from both sides. You got 2c2 is equal to, that would be 4/2 minus 1/2 is 3/2. Divide both sides by 2, and you got c2 is equal to 3/4. Yay, what a beautiful number. So your c1 is minus 1, c2 is 3/4. So go back to your original thing here, and your final solution, y is equal to e to the minus x over 2 times, c1 was minus cosine 2x plus 3/4 sine of 2x. There's your answer. Let's hope they get the same thing in the book. E to the minus x over 2 times minus cosine 2x plus 3/4 sine of 2x. Done. Okay. Now, I don't know if you remember back in trig. Did you take trig here?
No, I took it,
Okay.
UAB.
UAB. I don't know if y'all did graphing of trig functions. Okay. But this is called they have different names for it. I call it the envelope function, or the variable coefficient. And then those are your sine and cosine. They add to be some periodic function, but everything is enveloped within e to the minus 1/2. So therefore, out here they go crazily wild for very negative x's because this thing gets incredibly positive. But over here it narrows down and they keep oscillating, but always getting closer and closer to 0. And you see that from this. Because these things just oscillate back and forth. And this is actually very large. It's getting close to 0. But on this end, it's going wild. Okay, really wild. Are we through?
Yeah.
Yeah. All right. All right, so we got those two done. The next thing is 2 equations worth knowing. Is that all? Okay. The equations that are worth knowing? I think not, but 2 that they're going to say pay special attention to. So we'll pick up there next time. We didn't get a lot covered today, but we did get a lot covered, but not very much pages. Homework exercises here would include any of the odds 1 through 13 that are in the back, any of the odds 15 to 27 that are in the back, any of the odds 29 to 35 that are in the back, either 37 or 39 if they're in the back, 41 if that's in the back. Wait a minute. Yeah. I think we stopped there, and because that's, no, I'm sorry. No, maybe stop at 39. That's the bound. No, wait. Sorry, I went too far. Stop at 35, because the 37 is boundary value problems. We did those a while back, but not recently, so we'll hold off on those. All right, good deal. So you're off this week?
Today.
Today, anyway.
Just today. A whole lot of things going
Right. I'm sorry I wasn't in here right at the beginning. We could have got started right on the money, but it seemed like everything else was bothered.
I need some questions
Okay.
answered. I don't know if you want to record.
I can. There's no reason not to. Okay. I'll clear this. What you got?
Problem 7.
This is test 2.
Yes. You said it was Bernoulli's. It could be
I've
Bernoulli's.
got to find it first. Number 7. Oh, yeah. Okay. I remember it now. Okay. Okay. Number 7. Solve the initial value problem. Okay. Now, which way were you going to do it? Bernoulli's, or were you going
I haven't tried Bernoulli's yet, but I tried separation, and I'm not sure.
Let's see if we can do that separation. Let me write it down first. Number 7. dy dt plus 2 times t plus 1. I've been having a lot of trouble with my cataracts, so I'm having trouble reading, especially plus and minus signs. Y squared is equal to 0, right?
Yes.
And that initial condition y of 0
Negative 1/8.
is equal to negative what?
1/8.
Negative 1/8. Okay. All right, I could see that. Okay. So let's start by doing dy dt is equal to minus 2 t plus 1 y squared. Right?
Right.
Let's move that to the other side. Okay, now write it in differential form. dy is equal to minus 2 t plus 1 y squared dt. Right? Then divide both sides by y squared.
Y squared.
Yeah.
I was using 2y squared. Okay.
Yeah. Well, I guess you could, but I just assumed to leave the 2 with the t's. T's for 2, 2 for t. You for me. Never mind. Okay. Now.
I'm not that young.
All right. So we just integrate both sides then. Do you think that'll get you?
Yeah, I got messed up by doing the 2y squared, and I never got to the integration part of it.
Yeah. No, the t1 isn't squared, right? No. Okay.
I'm sorry.
T plus 1.
The 2y squared. I got messed up by doing that.
Yeah. It still should work, but it's just a little easier to leave the 2 over with the other side. That just works better. In fact, you could pull the minus 2 out of that integral and not even mess with it at first,
Yeah.
and just have a t plus 1 dt. And that's a fairly simple thing to integrate, I think.
How do you integrate dy over dy over y squared?
Okay. First, I don't like having denominators.
Never mind. I got okay.
How would you do?
Dy or y to the negative 2 dy.
Got it.
You're right.
Minus 2 integral t plus 1 dt. And I think both of those are pretty simple integrals to do.
At what point do you put? This is always throwing me off. At what
Yeah.
point do you put the
Plus c.
initial value back in?
Oh, okay, yeah. Okay. When you finish doing your integration, and this is frankly where it gets a little tricky, so this is going to wind up with a minus 1 over y, right? Minus y to the minus 1 is equal to, and there you're going to have and you're going to have there t squared plus 2 plus t squared over 2 plus t, and minus 2 is going to have that. Do a variety of things there. And then at the very end, do a plus C.
Plus C.
Okay. But this is still going to be a 1 over y, minus 1 over y. And actually, the minus here and the minus there, you can get rid of both of them. So, yeah. So 1 over y is equal to, and then you have some expression in t squareds and t's over here. Okay. Well, then you've got to flip this over and make it a y. And flip that over and make because you flip this, you got to flip that. Now, you have a plus c somewhere at the end. I would put it out there with that one. And then plug in when t equals 0, and that'll be pretty easy to plug in here. Because this is always only going to be in terms of t squares and t's. Mm-hmm. So that's going to be a 0, and then this is going to be a minus 1/8. Y is minus 1/8. So then you go back and whatever your c turned out to be, probably either 1/8 or minus 1/8 or something like that. Then you go back and plug in back into your quadratic that you had there, but it's going to be 1 over. So it's just that part is math, just accommodating all the, making sure everything's in the right place. If you get that far, you're going to get most of the credit. Yeah, but carry it on through, you can get full credit. Yeah, but when you get that, this will be in terms of y, that'll be in terms of t's. But 0's in for the t's and negative 1/8 in for the y. And you know, you have a plus c out there. You have to do all the evaluations, see what c turns out to be. Is that close enough?
Yeah, that got me a lot further than where I was.
Okay.
Because like I said, I never got to integrate it because I tried it dozens of different ways.
Yeah.
And every time it's getting worse and worse and worse.
Yeah.
Why am I'm not understanding something.
Yeah.
All right. How about number 8?
Number 8.
Number 8 looks to me, what is it? It's homogeneous, isn't it?
Okay. Now this is find an implicit solution of the initial value problem, this. Yeah, well, let's see what it does. It may be dy dx is equal to, you said homogeneous or homogeneous? Is that what you, yeah, it definitely is going to be that, I believe, because everything's in that power. X squared minus, no, y squared minus x squared, I wrote it right, but read it wrong, over xy, where y of 1 is equal to negative root 2. Okay. Now, it looks like that would be, but let's just write out and see. I'm going to go on and do xy dy is equal to y squared minus x squared dx. Okay? Is that what you were in the process of doing? Or?
No, not at all.
Okay. Now maybe homogeneous will be a good way to work, but let me then do this. X squared minus y squared dx plus xy dy is equal to 0. Okay. What I did, I moved this to that side, but rather than put a negative, I just flipped that. That made it negative. Okay. Now, what I was getting at is seeing if maybe this is also exact. Well, the partial of this with respect to y is minus 2y, but the partial of this with respect to x is an x, is a y. So no, it's not, but they're not far off, so you might be able to do that substitution to move that along. So that would be one possibility. So let's go back and do the homogeneous. And again, I want to, before I tell you something wrong, make sure, it's been a while, and that's not one I use a whole lot. Okay. Autonomous. Got to get in the right section here. Separable. It's not separable. Well, I didn't look at that. Nope, not separable. Okay. I think I did glance at it and notice that already.
How do you know that that's not separable? Because
well,
you just quickly look at it.
Okay. Because this thing, there's no way you can get this only in X or only in Y. This one, you could divide out a X here and move it over here. But this has X and Y's tied up with plus and minus, and that's not going to separate. Okay, so it's not separable. Okay, linear is here. Don't tell me I've already missed it. Exact. This is exact. And when they I'm trying to find which one you said the homogeneous, which is basically what we've got here, and you got to get it in the same form. Okay.
Page 73.
Yeah, 72 and 73, right. And what you do here is
Well, it doesn't work out, though, does it?
well, you do specifically either substituting y is equal ux or x equal vy. Try either one of them to fiddle with it and see if you can get it into separable. So let's try the y is equal to ux first. Okay. Okay, so this would then be an x squared minus u squared x squared dx plus x times ux dy equals 0. So this is x squared minus u squared x squared dx plus x squared u. Whoa. I forgot. We also have to deal with our d's here, don't we? Well, u is equal to y over x. Okay. Yeah, they changed it to DUs here. And this, let me go back to exact. Okay. And that would be what I would be tempted to do on page 69. Mu of x equal e to the minus, and do that one, or mu of y is equal to that one, to see which one works out best. and whichever one you get, then it should make it something that you can do exact. It's very similar to what you're doing over here with homogeneous cases, except here I think they wind up being something very, very similar to each other, okay? But for some reason, to me, the earlier was just a little easier to do. I may be wrong on that, and it's going to take some time to try it, but that's what I would try first. The integrating factor basically starts on page 68, but winds up on 69. See, we already did our m sub y and n sub x when we were testing.
Yep.
Okay, this is your m, this is your n, and m sub y would be minus 2y, and this is m sub y, and n sub x is just y. Okay, so try doing a mu of x, which is the e to the integral of n's. Again, my eyes are giving me trouble. It's m sub y minus n sub x. That's minus 2y minus y, right?
Where are you looking?
The page 69, number 13.
Okay, number 13 is mu of x equals
E to the minus, and your m sub y was minus 2y minus y, because it's minus m sub x, which is just y. And divide that by n, which is xy. Okay, I think this is a dx, yeah.
Yeah, it is.
Okay, and you see, I think that'll work out pretty nicely. E is equal to the integral of how do I write it? Let's take the minus on the outside, and then a y in here, and you have 2 plus 1, so that would be a 3. Okay, yeah, over xy, and the y's go out, and you can integrate that pretty easily. It's e to the minus 3 times the integral of 1 over x dx, which is just log x and e to it. Yeah.
I would not have gotten that.
Yeah.
I was going off in a totally different direction.
Yeah. Well, actually, I think the way you are doing was going to get you in the same place, but it might take you a lot longer to get there. Yeah. This one is, you just have to play around, try both of them. If neither one works, then go to do what you tried, because they all mix up pretty badly in there. But this, to me, was a little bit easier. But again, I had to go and refresh my memory on which do I put where. Those are the things not worth memorizing, looking up.
Yeah.
Yeah, for sure.
See, there's a lot of things, there's a lot of tricks that you've done, like reversing the x and y,
Mm-hmm.
and then, just flip. I never would have done that. I guess I would have eventually come up with it, but I would have come up with like a minus y squared minus x squared, then distribute. Yeah, okay, I would have come up with that. Yeah, okay.
Well, yeah, you would have eventually if you'd have subtracted this from and moved it over here. You had a minus y squared minus a minus x squared, which is plus x squared. So yeah, you would have been there whether you realized it or not. You'd have still been there. Yeah. But it's just a little easier just to do it that way. Yeah, that's school of hard knocks.
Yeah, that's a lot of
Hard
experience
knocks.
right there.
Right.
You've had more experience with this than I.
Yeah, right. Well, I've been doing Math 100 through differential equations for several terms now, many terms now, several years now. Not always everything, but yeah, that'll turn out to be a pretty easy thing to do, I think.
I was having a problem with this last one, Euler's method, but I don't remember what it
Okay,
was.
wait. I've got to find what I did with it. Here it is. Got it. Okay.
I don't remember why I was having a problem.
That's mostly grunt work.
Yeah.
Okay.
Yeah.
And Euler's method is in that last section, 2.6.
Yeah,
Is that right?
I think it is.
Yeah, 2.6. And you basically almost just set up a table and start going to town with it. And they tell you where to start. And you just have to write out all the pieces to it. And then, excuse me, I'll go back in. Here you're starting with y1. Y at 1 is equal to 9. So you're doing steps of 0.1. So basically you only have 2 steps from there.
Mm-hmm.
So you start with y of 1 is 9. And they tell you what y prime is.
So on this one, I'm not trying to find C.
I was trying to even see why. Oh yeah, there's y prime. Yeah. Oh, okay.
Oh. Okay, I see.
Yeah, it's
Okay, yeah, all right. All right, that's not as bad as
no.
I was overthinking it.
Yeah. What you plug in your function, what they call the function, that is your first derivative. So it's your first value, which is 9, plus your h is 0.1 times, and then you plug 1 into, okay, got to get first your x is 1 and your y is, and your h is 0.1. Your x is 1 and your first y is 9. So, so your first y would be your previous y, which is 9, plus 0.1 times and then you plug in this value, your x is 1, square root of 9, which is 3, so 1 plus 3, and yeah, I mean, so your first one would be, okay, the numbers are so confusing here.
Yeah.
1 plus, okay, so it would be your first approximation, y1, your y sub 0 is 1, okay. Your y sub 0 is 9, your x sub 0 is 1, okay, and your h is 0.1. So your y1, y sub 1 would be y sub 0, which is 9, plus h, which is 0.1, times, and then you have, this is where you do your function here. 1 plus 1 times the square root of 3. I mean, square root of 9, which is 3. So 1 plus 3 is 4. So that's what you do there. So it's 1 plus 0.1 times 4, which is 0.4. So your y1 would be 9.4.
Yeah.
Right. And then you do that again with that one, but I can't do those in my head because you have to then use a calculator for those. So the first approximation would be 9.4, and then using that one, come up with the second approximation.
Good. That made it a lot easier.
Okay. Okay. Good deal.
Thank you.
All right, then we'll close. If no more questions, I'll go on and close this out.